Well, number one is we're interested in applying the t-test to situations where we have two populations. We have samples from two separate populations. So far, we've only worked with a single population. We're going to want to know, well, when are we going to, what are the different situations we might use a two-sample t-test? Well, one of them is when we have two independent samples. If we have group A, completely different from group B, and we take a sample from each. New Yorkers versus Pennsylvanians. We take a sample examining some variables, some numerical variable involving New Yorkers, maybe average height or something like that, versus average height of people from Pennsylvania or some other country or something like that. Okay, so we have two, it's a numerical variable, and we have two separate populations. Well, what other situations might we have? Well, we might have situations where we have paired data. Paired data is a situation where we might take a single population, like, okay, I'm going to take a population of residents of a rehab center for stroke victims. And I want to track their progress. I have a kind of motor skills test that they do, and we're going to do some rehab work with them. And I'm going to take patient A and patient 1, and I'm going to measure their skill on this task before and after some intervention. Before and after some intervention, like some training or some physical therapy. And then I'm going to take patient A and maybe patient A and test how well they perform after a different intervention, right? And I'm going to test them before, and I'll test them after patient 2 before and after, patient 3 before and after, and so on and so forth. The difference there is that we're not testing a group of patients on intervention A and a different group of patients on no intervention or a different intervention, and then comparing the means of those two things. What we're doing is we're taking each patient and testing them under both conditions. So we have a before and after under both conditions. That's called a paired samples test. So we can see a difference. We're not really interested in what their score was before, what their score was at. We're interested in the difference in their score, how their score changed before and after. Okay, so it's different than having two different populations. A single population, you're taking readings or samples before or after. If you're testing a drug, for instance, you might put them on a placebo for 2 weeks and then put them on the drug for 2 weeks. And then with some patients, you do the other way around. You put them on the drug for 2 weeks and the placebo for 2 weeks and measure, say, their blood pressure at the end of each period when they were on that program, and then compare them. So blood pressure before and after under those two conditions. That's paired samples. So we can have independent samples or we can have paired samples. And we're going to get to real world examples of that. Okay, so we're going to have to identify when to use the two sample t-tests and z-tests and so on and so forth. When to recognize paired and unpaired two sample hypothesis tests, how to structure the null and alternative hypothesis, and how to construct confidence intervals for paired and unpaired tests. Okay, so one sample confidence, a single sample confidence interval using Z. Well, where would we come across that? We would only come across that when we know what the standard deviation sigma of the population is. And what's the formula for that? Well, it's X bar plus or minus the value of Z times the standard error, which is sigma over the square root of n, right? That's really what we've been working with all along here, right? Except that since we know sigma, we can use the value of Z. So we know right off the bat that Z is going to be equal to, if we want 95% confidence intervals, we're going to use 1.96. 99% confidence interval, we're going to use 2.58, and 90% we're going to use 1.64, right? So that's basically what we've been doing up to now. Okay, another version of that formula is on the bottom there. If you really look at it, it's just a combination of those two. If we want to know now, actually, let's take a look at that value Z. what does that value Z mean? Okay, so let's say that we have we take a sample, we find the mean of that sample, and we're comparing it to a known mean of another population, a single sample, basically a single sample test. Okay, we want to know how many standard errors apart they are, right? So we're going to take the difference between those two values, the mean of our sample and the mean of the population that we know, and we're going to find the difference. So let's say we're talking about blood pressure, and the mean of our sample is 120. The mean of the population we're comparing it to is 90. The difference is 30. We're going to divide that by the standard error. The standard error is the number of standard deviations, number of standard errors, number of standard deviations for the sample distribution that they are apart. What is that equal to? It's equal to sigma over the square root of n. We're going to take that divided in. So let's say the standard error is equal to 15. So 30 over 15, it's two standard errors apart, the mean x bar and the known mean of that population mu for a single sample test. They're two standard deviations apart. If you look down on the bottom there to this distribution, this is a distribution of, is that sample means or populations, or the population blood pressures? What is that? That's the sample means, right? We're dealing with, when we're dealing with the t-test, this is the distribution of that z-score we have. Remember, it's standard error that we're dividing by, not standard deviation. So that's the distribution that describes the width of the spread of the sample means, right? So that's the sample distribution. So basically what that's telling you is that if you get a z-score, if the mean and the value of x bar are two standard deviations apart, right? That they're that distance away, then you would only get that big a distance 2.5% of the time on the low side, and only that big a difference on the high side, 2.5%. So you would get only that extreme a difference between the two means, the one you got from the sample and the one you're comparing it to, only 5% of the time. That's what the z-score tells you. The z-score tells you, well, what if the z-score were 2.58? If the z-score were 2.58, it would be all the way out here. Remember, 99% confidence interval is 2.5. That would be only half of 1% there and half of 1% there. You would only get that big a difference, less than half of percent of the time, right? Now, these tails here, theoretically, they're asymptotic, which means they don't really ever touch this line on the bottom, right? They don't really ever really go to zero. They go to like ridiculously small, don't ever really go to zero. Well, what does that tell you? That tells you we have to make a judgment. I could tell you that the blood pressure, average blood pressure, remember that the standard error was 15. I could tell you that the blood pressure in our group of our X bar of our sample was 150, and the normal blood pressure that we were comparing it to, the other group, was say 90, and that's a difference of 60 over 15. That's 4. That's, am I right? 4 times, right? That's a z-score of 4. That's all the way down here, or all the way over here, right? So what point can I tell you that that's impossible? They can't be from the same population. They got to be different. How big a z-score do we need to be able to say that they're absolutely positively not the same? We can't, because there's always an infinitesimal little tiny possibility that they're the same. Not only that, but they really have to be very different, and we really have to have a gigantic sample size to be able to do that. So we got to make a judgment. What will we find acceptable? If we say, you know, we got to be 99% sure. Well, unless the mean is this far apart, 2.58 z-score, we can't say with 99% certainty that they're different. So most studies will be satisfied if you'll only get that outcome, that distance of that distance between the two means, you'll only get it less than 5% of the time. That's good enough for you to reject the null hypothesis and say that they're different. Did I do something there? Okay, that's what we're really after there. We're really after figuring out where we can say that that's true. So there's a couple of ways. Oh, excuse me, that's on my computer here. You know, you get too many keyboards, you don't know what the hell to press. Okay, that's really what this is all about. If we don't, if we know the sigma, the standard deviation of the population, we can use Z. If we can use Z, we can look up, if our Z comes out to be 1.63, we can look up for 1.63 what the probability that we would get that extreme a difference would be from the Z table. So we can look up on the Z table that area is, say, 7%. But, you know, it could have gone the other way around, too. So 7%, you always double it, right? Because it's alpha, that's alpha over 2. And this is two, this is over 2. So 14% at 1.64 would be it would be 5% here, 5% here for 10% total of 1.64. We could look up on a Z table and see that represents a 10% chance that you get that big a difference. Too much of a chance for us to say that they're different. Got to be less than 5%, right? So when we got the Z-score, we can actually look up on a table what the p-value is, what the probability that we would get that extreme a difference would be. That's what that p-value or significance means. How likely it is that if the null hypothesis is true and they're really the same, that we would accidentally get that big a difference, right? So if we don't know what sigma is, then we're relying on the t-score. If we calculate it manually, we don't have a Z table that shows all the different possible values for t. We only have Z t tables that show the value for 95%, 99%, 90%, right? So in that case, when we substitute t for that, when we don't know the standard deviation of the population, we don't know the standard deviation of the sample, when we substitute Z for that and use t, first what we do is we look up the critical value of t. What value of t gives us 5% on either side of this? And it's different for every sample size, every degree of freedom. So for instance, if your value of t for a sample size of 15 is 2.06, that's the number, that's the distance, that number of standard errors. That t is that z instead of z, that t is equal to, and it comes out to it comes out to more than 2.06. It's further out on here than you need for 5% chance, less than 5% chance of that occurring. So you really don't know the exact p-value, but you know it's going to be less than 5%, so you can reject the null hypothesis. They're far enough apart. When you use SPSS, it gives you the t-value, but it also gives you the calculation for p as well. Last question on the exam showed you a chart. It shows you the t-score, and it showed you a p-value. Two ways you could have solved that problem to tell me if you could reject the null hypothesis. One is to look at the sample size and look at the value of t and see what the critical value for that sample size is, and look at the value that was calculated by SPSS. If the value calculated by SPSS is bigger than the critical value for that sample size, you can reject the null hypothesis because it's further apart from the mean that you would compare it to. But you could also just look at the p-value. The p-value tells the probability that you get that big a difference. You know, if you get that, you would get that big a difference if the null hypothesis were true. And in the case of the sample in the exam, it was 8%. So there's an 8% chance you could get that big a difference just by chance, even though the two populations have the same mean, right? So you can't reject the null hypothesis because you want to be at least 95% certain, not just 92% certain. Okay, so that's really what this is all about. That's really what we've been doing for the last 2 or 3 weeks. Okay, here's an example of the t-test. Okay, paired or dependent samples, independent samples. Paired or generally also called dependent samples. Unpaired or independent samples, 2 groups basically, 2 different groups of people. Okay, independent samples, birth weights of unrelated boys and girls. Laboratory results from 2 different participants in a clinical trial. Person A, person B, one took the placebo, one took the drug. Comparison of household health care costs in the United States versus Canada. Different populations, taking samples from different populations. Paired or dependent samples. Difference in birth weight of twins. That's an interesting one. pre and post laboratory results for each participant in a clinical trial. In other words, before they took the trial, after they took the trial. Ocular measurements in the right eye and left eye of the same subject. Okay, same person, only one person, not two subjects. Stress measure scores in twins of husband and wife. He's really chasing, the very last definition of a paired sample here. Measurements from two methods of conducting an assay on a patient sample. Again, a lot of ways to get a paired sample. Okay. Okay. Compare average heights of males and females, paired or unpaired. Average heights of males and females. Right? Is that two different groups or one group? Two different groups. It's unpaired, right? It's independent samples. Compare the anxiety level of individuals before and after an intervention. That's one group. Each person is measured before and after. So that's a paired sample. Their score before and the score after, right? Good thing about that is that, think about it. When you do an independent sample, right, and you sample men from Brooklyn, men from France, right, and you say to yourself, I'm going to measure something like blood pressure or something like that. You randomly sample 100 people in Brooklyn, 100 men in Brooklyn, 100 men same age group in France, and you compare the two of them for some nutrition issue or something like that. Well, there's a lot of other stuff going on there. You might wind up finding out that the sample from France, a lot of that, 30% of them or 40% of them were smokers. From Brooklyn, only 20% were smokers. That's kind of a confounding variable that's in there, right? If I randomly sampled 100 people from Brooklyn and 100 people from Queens, and then I sat down and did a study, when the study's done, I might say, oh my goodness, look what happened here when I did the study. In Queens, 60% of the participants were women. In Brooklyn, only 30% of them were women, just by chance, right? So there's a lot of extra variables. Now think about when we do a paired sample test. It's the same person before, take the drug, after. What's the difference? That's the same person. Same BMI, same weight, same smoking habits, same everything, right? So you eliminate a lot of confounding factors when you do a paired samples test. So they can be a lot more powerful, can't they? Okay. Okay, relation one sample t-test to a paired sample t-test. You want to know something? Interesting thing about a paired sample t-test. I take a person's blood pressure before I give them a drug, and I take it after I give them a drug. And I see, let's see, the difference, it's 120, and there it's 100, so it was minus 20. Then the next person, before and after, minus 10. The next person, before and after, plus 5. Next person, before and after. All these people that took the drug, I see that, what their scores were before and after. And I said to myself, gee, was there a difference here? If the drug had no effect, instead of looking at each individual's before value and after value, let's only look at the difference, right? So if there was no effect, the drug had no effect, what would you expect the average difference between the person's blood pressure before and after to be? 10, 20, 30, 40, 10, 80, 70. If there's no effect of the drug, the difference before and after is going to be 0, right? So really, a paired samples t-test, all you got to do is take the differences and compare them to 0. So what are you doing? You're doing a single sample t-test with a comparison to 0, right? So you remember when you start up SPSS and you're doing a paired samples t-test, what number is in there by default? 0, because that's most often, when you do paired sample t-test, what you're going to wind up. A single sample t-test, often there, you're doing it because you're doing a paired sample test and you're comparing it to 0. Yes? I'm sorry, say it again? I'm not sure I know anything. You said something. Wait up 4 weeks ahead of us. There's something called regression median. That's why regression is called regression, right? Because the guy who developed this tool called regression. That's what he was investigating. That really doesn't apply. That's going to be something later on. That's kind of in a situation like, let's say you have two really tall people, right? They're both 6'8". Male 6'7", and male 6'8", right? Are they likely to have a child that's tall as them? Well, in a lot of situations, no, because by chance, remember a lot of this stuff has to do with chance, not just a lot of complications with inheritance. By chance, it's unlikely you're going to have kids 6'9". It's more likely to have kids 6 that may be tall, but not as tall as they are. You know what I'm saying? Like, in other words, when you do these combinations, it's likely that the result is going to regress towards the mean rather than become more extreme. So, as you can imagine, I mean, they're very, very tall, and if you're very short, it would be likely that your offspring would be more likely to be taller than you than shorter than you, because on average, all people are taller. Most people are taller than you. But yeah, that's kind of a different thing. Right here, we're just concerned about whether or not we can demonstrate a difference in an average for a population versus a set number or two different populations. Okay. Okay, t-statistic for two independent samples. Okay, we have treatment and control. That, like these, a lot of times you're doing experimental studies this way. You're taking a measurement, you're putting people into a certain environment or an exposure or something like that, and you're measuring one group, has experiences the exposure, the other group maybe doesn't experience the exposure. You wind up with two means. This group has remember we're talking about populations for now. This group has this population, people who would take this drug, or the control group, or the treatment group, and they would have a certain average, whatever medical measurement you're making. The other group, population are people who are not ever going to take the drug, and they're your control group, your control population. You're going to take a sample from the general population, and you're going to divide these people randomly up into two groups. One of them is going to be your treatment sample. The other one's going to be your control sample. Control sample is going to get placebo. Treatment group's going to get the actual drug. Okay, so what's our null hypothesis here? Well, our null hypothesis is if the drug don't do anything, then the mean for the population of people who would take the drug is going to be the same for the mean of the population of people who don't take the drug, right? Drug has no effect. Means are going to be the same. Our alternative hypothesis is that the mean for people who don't take the drug, for people who take the drug, is going to be different than people who don't take the drug. The drug is going to have an effect, presumably a positive effect. That's going to be mu c. It's not equal to mu t. Mu control is equal. Another way of saying that is mu c minus mu t is equal to 0. So you can do it either way. It's not equal to 0. So you can set up your null hypothesis either way. Mu c equals mu t. Null hypothesis mu c minus mu 1, mu t is equal to 0. They both say the same thing, right? If the two means are equal, right, then when you subtract one from the other, it's going to come out to be 0. That's your null hypothesis. Okay, and again, I think this came up before. Your null hypothesis is always deal with the mean of the population. It's always mu is equal to mu2, or mu is not equal to mu2. Never x bar is equal to or not equal to. It's always, we're always talking about the population, because that's what you're using a sample to test your theory, your hypothesis, but you're really concerned about the population, not your particular sample. Your sample is just a means to get there. Okay, so now we've got a problem. Let's take a look at dealing with, how did we do a single sample z-score, a single sample t-test? They're really the same thing, except with the z-score, we know the standard deviation of the population, no sigma. So how do we figure out what this was? Well, we took the difference in the means of, we took the difference in the mean of the sample minus the mean of the population we know about, x bar minus mu, and put it over the standard error. Standard error is equal to sigma over the square root of n. We know the sample size that we took, right? Well, that's great. The only problem is now we have to deal with two different samples. We don't know the mu for the population to compare it to. We don't have, so now we have X bar 1 and X bar 2. And that's what we got to compare. We can't compare X bar 1 and mu 2 because we don't know what mu 2 is anymore. So you got to compare the two of them. So if you look at the bottom formula there, X bar 1 minus X bar 2 minus X bar 1 minus mu 2 minus mu 1. We're looking at getting that 0 that we're looking for, the difference of 0 that we're looking for. But to tell you the truth, mu 2 minus mu 1 in our null hypothesis was equal to what? 0, right? So we can just drop that out right now. We can eliminate that. So really, we're looking at X bar 2 minus X bar 1 over the standard error. Okay, so I took a sample. Let's say I know the standard deviation of the population. Standard deviation of the population of population 1 is 50, and standard deviation of population 2 is 35. Okay, they have two. They each have their own, and the mean for sample 1 was sample 2 was 100. Mean for sample 2 is 20. Let's say. Okay, great. So 100, let's say 120. 100 minus 120 is minus 20 over the standard error. Okay, so standard error is sigma over the square root of the sample size. Well, which sigma do I use? Do I use the sigma for group 1 or for group 2? And which sample size do I use? Do I use the sample size for group 1, group 2, or do I combine them? I got a problem. I have two different samples. I'm going to wind up with two different standard deviations. Here's the real world example where we don't know what sigma is for the population. So we wind up with X bar 2 minus X bar 1 over the standard error. So we need a way to find a single standard deviation for us to be able to know what the standard error is. So what we do is we combine them. We weight the standard errors. Okay. So this is an example where we take, this is a situation where we're not adding them all together and recalculating. We're taking the standard deviation of sample 2, squaring it, that's the variance, remember? Dividing by sample size for group 2, adding it to the standard deviation of group 1, squaring it, and dividing by the sample size for group 1, adding them all together and then finding the square root of that. So that's kind of taking this standard deviation, dividing it by the combined sample size, right? Look, kind of like that. So what we're doing is we're dividing by a weighted version of the standard error. So on the bottom there, we're accounting for the fact that the samples could have different standard deviations and they could have different sample sizes. But all you have to do is apply that formula to do your t-test. Okay, so we're going to wind up doing some examples of that. Okay, on the other hand, we could do this another way too. Okay, we can do this by pooling the two standard deviations together. In other words, let's say that I have a list of 10 numbers from sample A, 10 numbers from group sample B, right? Why not just take those two groups? If we can say to ourselves, gee, you know, I think really they pretty much have the same standard deviation. Why don't we just group the two of them together, find the standard deviation for 20 numbers instead of 10 numbers, right? By just combining them, pooling them and just combining them. That's a possible way for us to do this also. We're going to get, when we get into some examples, we're going to start to see where the time is that we would, at what point we would use either one of these two methods to do this. So basically when we're doing a t-test with two sample means, instead of one sample mean, all we're doing is substituting an X bar for the mu that we had before, right? It's X bar 1 minus X bar 2, right? But on the bottom of that equation, things get a little bit more complicated because we have to combine the standard deviations for the two groups. Right? Okay, and I will get to this in more detail. Okay. I'd rather do this when we're working with a real example. Okay, now, one of the things that it would be very nice to be able to say is that there is that if we can show that the two confidence intervals for one sample and another sample do not overlap, right, that we can say with 95% certainty that the true means of those two groups are different. In other words, we can reject the null hypothesis if the two confidence intervals don't overlap. Problem is with that, we have some issues with that. Okay. Instead, it's more legitimate to compare the two means in terms of the standard, in terms of the z-score between the two, z-score to t-score between the two means. So you won't see us checking for overlapping confidence intervals when we're comparing two means. We might do it when we are doing a single sample test because we know one of the values of the two means. I have another page that I have a summary page that I'll give you that I think is a little bit easier to work with. Significant tests. Okay, some limitations of these kinds of significant tests. One of them is when the sample size is very small. Remember the central limit theorem tells us that we don't really need a perfectly normal distribution to apply these various rules that we're using for comparing means or for determining confidence intervals. Problem with that is when the sample size is very small, we really can't depend on the central limit theorem to produce a result for our sample means that are going to be perfectly normally distributed, which is what we're basing our probability of rejecting the null hypothesis on. So we got to be a little bit concerned when sample is very small that we might miss some results that we could that we might otherwise have caught if we had a larger sample size. Now we've a situation where we could have rejected the null hypothesis with a larger sample size. When sample size is very large, you can wind up with a situation where it's very easy to reject the null hypothesis, but the result is not clinically significant. When you have a very large sample size, you might have a population A and a population B, and you might find with a very large sample that the blood pressure of population A is 100, blood pressure of population B is 99, but your sample size is so large that mathematically you're able to just barely say, reject the null hypothesis, say, oh yeah, they're statistically significant that population A is different from population B. But clinically, the difference between a blood pressure of 99.5 and 100 is not clinically significant. Right? And it may not even be real. It just may be the power of all those numbers of that very, very large sample size may give you that effect. Okay. Okay, so the p-value, remember that p-value? That's the probability that we would get that outcome, that big a difference between the two means if the null hypothesis were true. So let's say that our p-value is 3%, 0.03. The chances we would get that extreme a difference between those two values is 3%, less than 5%. So typically we would reject the null hypothesis and say that they're different. Let's say that the p-value came out to be 6.6, 60%. Would that be an indication that the null hypothesis is true? Because you would get that result 60% of the time if you could get that result 60% of the time if the null hypothesis is true. But we can't use the test that way. It's not designed that way. That's one of the reasons why you never say, when you fail to reject the null hypothesis, you never say that you accept the null hypothesis. Right? You just simply fail to reject the null hypothesis. Okay. Okay. I think there was one more that he had here. You know what I'm going to do? Let's take a 5-minute break. I'm going to play that video, the presentation on the data set for New York City Community Health Survey. I'm going to play that video so we can get a look at it. Let's take a break. Take a quick break. Okay, and I'll get that queued up. And for you guys online, I'm going to pause our recording. In 5 minutes, I'm going to start that video. I think it's about maybe 10, 15 minutes long. And then we'll come back and we'll work on the lab work.
This conference will now be recorded.
I think I'm recording again. Okay, so that's a single sample test. The next ones are harder. So I'm glad I remember at least to start recording again at this stage. Okay, so let's take it one step further now. Okay, I'm gonna get rid of this. Well, no, I don't want to exit. Okay, just get it out of the way. I don't know why that's asking me that. Okay, I don't know what that means. Go away. Something crashed there. I'm forcing to quit. Okay. Let's go back to that exercise. Okay, next example. 2 sample hypothesis tests with roughly equal variances. You know, I could put these into Excel and try and analyze them. So you remember when we have a 2 sample t-test, we have a little bit of an issue with, I'm going to get a I don't have a sigma for either one of these groups. All I have is a standard deviation I'm going to get from these numbers. Which one should I use? And can I pool them together? Well, we're going to run into a problem with that. Sometimes we want to pool them, sometimes we don't want to pool them. So there's a sheet on Blackboard which discusses the various situations you might find yourself in, the variations of the t-test that you might wind up encountering. Okay, so here's the first variation. The standard deviations of the 2 samples that you take are assumed to be equal. What do you do when you assume them to be equal? You can take, when you assume that the standard deviation of this group, of this sample, is the same as standard deviation of this sample, and they're the same, you can say to yourself, hey, let me combine the 2 groups to calculate a single standard deviation and be more accurate, have a standard deviation that's more likely to represent the population standard deviation. But in order to justify that, you have to make the assumption that the standard deviations are equal to begin with, and that the little differences between them are just due to chance, right? So what do you do then? What you do then is you state your null and alternative hypothesis. Okay, and I'm going to do that right now. If I can click, it will let me click into this. Oh, it's PDF file, I can't click into it. Okay, I would type into this, I would then say, my null hypothesis is mu for group 1 is equal to mu for group 2. My alternative hypothesis is mu for group 1 is not equal to mu for group 2, right, or population 2. So, okay, good. So now determine your level of confidence. What's alpha? What's our level? What do we want our level of confidence to be? What do we want to be? 99% sure, 95% sure, 90% sure. Most of the time, we're usually happy with 5%. Alpha is equal to, for us, we're going to state alpha is equal to 5%. We're only going to reject the null hypothesis if there's less than a 5% chance that we would be wrong. Or in other words, get that extreme outcome when the null hypothesis is true. Okay, so okay, we've done that. Now, calculate, since we made the assumption that the 2 standard deviations were equal, we're going to calculate a pooled standard deviation. Well, the problem is one could have one sample size, one could have a different sample size. It gets a little complicated. We want to have a weighted average of the 2 standard deviation of the two samples. So we calculate a pooled standard deviation. What's that equal to? That's equal to the square root of sample size minus 1 times the standard deviations, the standard deviation squared, the variance of sample 1, plus sample size 2 minus 1 times the standard deviation squared of sample 2 over n1, the sample size 1 plus sample size 2 minus 2. A little complicated, right? But it's just a formula. Don't worry about it. It's just something you got to plug numbers into. You know what all these things are. S1 squared is the standard deviation for group 1 squared. S2 squared is the standard deviation for your sample 2 squared. Okay, so I'm going to give that a try right now in Excel. I'm going to move this over here. I'm going to open this data in Excel. And again, if you want to go along with me, you have this on Blackboard. Here's our data. Okay, so I'm going to go down here. I'm going to find the mean. Okay, this is going to be X bar equals, okay, average, parentheses. The average of these numbers is 10 equals average, parentheses. And the average for females is 7.55. Okay, this is X bar 1 and X bar 2. X bar M and X bar F. Okay, what about standard deviations? Standard deviations for the males and the females. Okay, let's find out what that is. Equal to standard deviation of these numbers and the standard deviation of those other numbers. Are they equal? They don't look that equal, do they? 2.7 and 1.9. We're going to have a funny rule. We're going to have some sort of rule that we're going to use to decide. They're never going to be equal, right? We know they're never going to be exactly equal because when you take samples, random samples, one group and another group, the chances, even if the standard deviations, two populations are equal, the chances they be exactly the same in your two samples, tiny, right? So we're going to use a rule that if one is not double the other, we're going to say they're equal. That's close enough for us. So is one double the other? No, it's not, right? 1.9 double would be 3 points, right? It's not double, right? Window. So we're going to assume that they're equal variance. You got a question back there? Okay. So we're going to assume that these are equal variances. So we're going to apply that formula we just looked at. So I'm going to bring that formula up over here so we have it alongside. So we can look at it as I do this. Okay, let me find it if I can. Here it is. I'm going to put that over there, and I'm going to bring this up over here. Okay, so I'm going to calculate a pooled standard deviation pool. And that's going to be equal to, and I'm going to do the top of this equation first. It's going to be equal to the sample size minus 1, 8, times the standard deviation squared for males. We need to move this over just a little further. The standard deviation squared for males is this number. Whoops. Did I just do something wrong there? Pooled standard deviation is equal to 8 times the standard deviation squared. I'm just going to do it simply. I'm just going to multiply it by itself twice. Okay, plus I'm going to add to that the same thing for the second group. The sample size is 8, is 9, minus 1 is 8, times the standard deviation for that group squared. Times, oops, forgot to put in, yeah, I got that, okay, times this, times this, close the parentheses. Okay, and good. And I think I can enter and I got it. Okay, so the top part of that equation is 90. What's the bottom part of that equation? N1 plus N2, that's 9 plus 9 minus 2 is 18 minus 2 is 16, right? So I'm going to now say, okay, I'm going to divide those two. That's equal to 90.2 divided by 16. And that's equal to 5.363. And now I'm going to find the square root of that number. And it comes out to be 2.37. Look at that, 2.37, 1.94 is 2.73. It's in between those two numbers, which is what we would expect, right? That's my pooled standard deviation for those two groups. Why did I do that? Because I'm assuming that the two populations have the same standard deviation, that they're equal. Okay, so what do I do now? Well, now I do my t-test. And here's my t-test. I take x bar 1 minus x bar 2, same as always, and divide it by the standard error. The standard error in this case is the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Okay, good. Let's do that. So my t value for t, right, is going to be equal to, going to be x bar 1 minus x bar 2, okay, which is going to be equal to 10 minus, oops, 7.55. Okay, and then on the bottom of that is going to be my pooled standard deviation, which is 2.37 times this times the square root of 1 divided by sample size 1, which is 8, plus 1 divided by sample size of the other, which is 8, happens to be 8 also. Close the parentheses. We're going to find the square root of 1 over 8 plus 1 over 8 and multiply it by the pooled standard deviation. And that comes out to be 1.18. So my t value comes out to be the top part of that equation divided by the bottom part, nominated divided by the denominator. Okay, it comes out to be 2.058. Okay, so now, gee, now I got a t-score, and I got to know whether it's large enough for me to reject my null hypothesis, right? So I need to know the critical value of t for this sample size. Well, there's two samples though. So what's the sample size? Well, if you look down further in these instructions, calculate the degrees of freedom. The degrees of freedom are n1 plus n2 minus 2. Okay, so the degrees of freedom, we want the t-score for the degrees of freedom equal to 16. 9 and 9 minus 2, right? And that's going to be our critical value of t. And what is that? Well, what is the critical value of t for a degrees of freedom of 16? Where'd it go? I still have it here somewhere. There it is. Okay. There it is. Over here. Critical value t for 16 degrees of freedom equals 16 is 2.12. So my critical value of t is equal to 2.12. What's the value of t that I calculated? 2.05. It's less than my critical value. Can I reject my null hypothesis? I want to see heads nodding. Hybrid nod, no, you can't reject your null hypothesis. Why? Because I didn't exceed my critical value. They're not far enough apart. And my p-value is going to be less than more than 0.05. Yes. I'm an old man. You got to talk louder than that. I used 8. Oh, no, wait a second. Did I use 8 or 9? That's a good question. Did I make a mistake there? Hang on a second. I used 8. What was it? N? I think it's N. I think you caught me in a mistake. Yeah, yeah, it should have been 9. I was thinking degrees of freedom. You're absolutely right. Hang on a second. Let me correct that. 9. Good catch. 9. So t becomes 2.18. What happens now? That was a good catch, because look what happened. What's my critical value of t? 2.12. What did I just calculate t to be? 2.18. So my critical value of t is bigger, is my calculated value of t is bigger than my critical value. That means my values, my means are far enough apart for me to say that the population means are probably different. In other words, reject my null hypothesis. Everybody nod their head. Can I reject my null hypothesis? Yes. Why? Because I exceeded the critical value of t for that number of degrees of freedom. Does this complicate stuff having to do all this extra calculations and so on and so forth? Yes, it does. But you wind up, it's really doing the same thing, except with a little bit more manipulation of numbers. You're really going through the same exercise again. Okay, now, what might happen next? Remember I mentioned to you that if one standard deviation, the standard deviation of one group is not twice the standard deviation of the other group, other sample, you assume that they have equal variances, right? You can assume that they have equal variances. Do it the first way. Well, what about if the difference is more than double and they're unequal variances? You can't do that. Now, how do you handle that when you have two separate samples? Okay, that's our next problem. Okay, so state your null and alternative hypothesis. Mu1 is equal to mu2. Right? Mu1 is not equal to mu2, alternative hypothesis. Determine your level of confidence. What's alpha? Alpha is going to be 0.05 again. Okay. Using the standard deviation, the means for each sample, calculate the t-value. Well, now, if we assume that they're not equal, this is what we're going to use to calculate our t-value. And this bottom part is going to be our standard error. Our mean 1 minus mean 2, mean x bar minus 1 minus x bar 2, just like before, divided by the standard error. There's our standard error there. It's going to be simpler. It's going to be standard deviation of group 1 squared over n1 plus standard deviation of group 2 squared over n2, and we're going to find the square root of that whole thing. So let's do that using Excel. And I'm going to open up the data set for, I have a separate data set for this, I think. Okay. Two sample t-test with unequal variances. That's the one I want. Two sample t-test, unequal variances. Okay, good. Let me get rid of all this junk here. I'll just try this. I don't know what that's there for. Okay, I'm going to find x bar 1 and x bar 2. And I'm going to find standard deviation for group 1 and standard deviation for group 2. Okay, so the mean is equal to average. Parentheses, I'm going to find the mean for all these numbers. And 10, and I'm going to drag this across. And that's 7.55. And the standard deviation, parentheses, and 14, 2.73 equals standard deviation, parentheses, and this is going to be 1.01. I changed the numbers a little bit there. You notice there's less variability in the females than there was before. Are the standard deviations greater than or less than double each one or the other? It's greater than. So now I can't say that they're equal anymore, can I? So now I have to use the rules for doing a t-test for unequal variances. So I'll do it. Okay, let me get my sheet out here in case I don't remember how to do it. Okay, I'm going to make this narrower. Okay, so how am I going to do this? I'm going to calculate the top of this, t. Got to calculate what t is, right? Okay, so the top of this is going to be x bar 1 minus, oops, escape, oh boy, Read that up. Hang on a second here. Okay. So t, the top of that equation is going to be equal to x bar 1 minus x bar 2, oops, minus x bar 2, right? That's going to be the top of that equation. The bottom of that equation is going to be equal to, what's it going to be equal to? It's going to be equal to the square root, and you don't have to necessarily do this all in one shot. You could break it down into smaller bits. The square root of the standard deviation for sample 1, which is this, times itself, squared. You could also use it up carrot if you wanted to, over the sample size, which is 9, plus the standard deviation group 2 times itself over the sample size, which is 9. Okay, and I got a plus between these. So I need this. This should resolve this and this together and then add them together. This should work, but I may have to go back and put in some parentheses if it doesn't. And that comes out to 0.9734. That's my standard error. That's the bottom of that equation. In other words, the top is 2.44, the bottom is 0.97. So what is the value of t? The value of t is equal to 2.44 divided by 0.97, which is equal to 2.51. How many degrees of freedom do I have here now? When I was using equal variances, what did it tell me to do? It told me to do n1 plus n2 minus 2, right? So 9 plus 9 minus 2, 16. How about now? Well, you know, this was so much simpler doing the standard deviation this way for two samples. It must be a way that statistics is going to punish us. There is the formula there for figuring out the degrees of freedom. That's some formula, right? Pretty nasty. Most of the time, what people will do instead of figuring out that formula is they will say, I'm just going to take the sample size of the smallest group and subtract 1. That's a very conservative way of handling this. So 9 minus 1 is 8. I'm just going to call it 8 degrees of freedom. It's possible you may fail to reject the null hypothesis when you could have, but if you're close, you can always go back and do this calculation because you're close, and you want to know whether you really could have done it if you've done the calculation. So the degrees of freedom is going to come out to a weird number if we do it that way. Using our quick rule, we're going to say 9 minus 1 is 8, right? So 8 degrees of freedom, right? So our calculated value of t is that our t critical, which is for 8 degrees of freedom. Well, what is that? You know, I should remember, right? We just did that recently. But let's say I don't remember. Here we go. 8 degrees of freedom. 95% confidence. It's 2.306. I know I recall that number. 2.306. That's our critical value of t is that. What do we calculate? 2.51. 2.51 is more than our critical value of t. So what can I do with my null hypothesis? I can reject it, right? Because I exceeded my critical value of t. And what is my p-value going to be? I don't know what my p-value is, but I do know it's one of two things. It's either more than 5% or less than 5%. Which one is it, more or less? It's less, because now, as your t-value gets bigger, the probability of you being wrong if you reject the null hypothesis goes down. So your p-value goes down lower. When the t, if our t critical, if our t calculated was exactly 2.306, we would know our p-value is exactly 0.05. That's what our critical value of t means. Since our t-value calculated is above 2.05, 2.306, right? Since it's above that number, we know the p-value has to be smaller. It's less likely because they're further apart, right? There's less tails left on either side because they're further apart. Okay, I'm going to do the same thing in SPSS. I have the same data set. I'm going to do the same thing in SPSS. Okay, those are two data sets. Notice female and male. Notice how SPSS organizes the data differently from Excel. You have two variables. Each person has a number and a gender, number and gender. So you have two columns instead of two separate columns of numbers, male and female. Now you have a column of numbers and a column that indicates gender. That's how SPSS is going to organize this data. So I'm going to go up here to analyze. What am I doing? I'm comparing means. So I go down here, and now I'm going to go down to not one sample t-test, but independent samples t-test. Both of these tests that we've done are independent samples t-tests. Okay, and I'm going to say, okay, I am going to move the values, the numbers, whichever variable represents the numbers, into the test variable, and into the grouping variable, I'm going to move gender. Well, you know, there's a problem here. SPSS wants to know what the numbers are. I'm going to close this for a second. I'm going to cancel this. If I go to the variable view, if I look at gender, gender is a numeric variable, right? It's a nominal variable. It's identified as a nominal variable, right? The name, female or male, not really a number, but it's represented by a number. Well, if I go over here to values and click down, I can see that the value 1 represents female and value 2 represents male. SPSS needs to know those numbers. You can tell it that we're going to break it up into two groups, males and females, but you have to tell it that those are represented by the number 1 and 2. I'm going to go back here. You can also do it this way. Just go to view and say turn off the value labels, and you see the 1s and 2s. Turn back on the value labels. You see 1s and 2s. That's why you code the data. Okay, so I'm going to go back here, and I'm going to say analyze, compare means, two independent samples, males and females, put the values in here, put the grouping variable here, right, and define the groups. And the groups are 1, the number 1, and the number 2. We know they represent male and females, but that's the way SPSS organizes it. I'm going to click OK. It's going to come up with an output table, output window. And let's see what our output window tells us. Oops. Move that up a little bit. Okay, what's our t-score? Our t-score is 2.511. I think that's approximately what we got before, right? Okay, and what is our p-value? 0.23. That's less than 5%. Both our t-score and our p-value both say that it's going to be, we're going to reject the null hypothesis. The p-value or two-tailed significance is less than 5%, and the t-score is bigger than our critical value for the 16 degrees of freedom. Now, that says 16 degrees of freedom. This one down here says 10 degrees of freedom. What is that all about? It's actually did two tests, didn't it? It did a t-test here, and did another t-test on the bottom line. It does that all the time. What it does is it makes both assumptions. It says, I'm going to do this assuming equal variances. I'm going to do it again assuming unequal variances. I'm going to do both tests, right? I'm a computer. I'm doing nothing else anyway. I'm going to do both tests, right? So it does both tests. It's up to us to decide which one to use. Well, we decided that, gee, one had a standard deviation of 1, the other 2.7. We're going to use the test that is for unequal variances. And that's the bottom line. Equal variance is not assumed. Top line is equal variance is assumed. Bottom line, equal variance is not assumed. And you'll notice 2.51. And look at the degrees of freedom. 10.152. It's not a nice even number. That's because SPSS actually calculates that ridiculous formula, right? We assumed 8 because we were being conservative, and 1 minus 1, right? But SPSS actually calculated it's 10.1. That's why you get such a weird number for degrees of freedom. And the actual p-value is a little bit different for these two. It's actually 0.31 for equal variance is not assumed. Okay, so now the other thing you may notice here is that there's really an extra box here. I'm going to walk away from you. At home, but you see how the t-test really starts here. You got t, degrees of freedom, significance. Those are the names that you're interested in. T, degrees of freedom, significance. Right, this is the t-test over here. So what is this part over here? These two boxes. Yeah, so anyway, so Levine's test for equality of variances, right, is this little box right here. What is this telling us? This is telling us that SPSS is applying this test to tell us whether we should use equal variances or unequal variances. Okay, so how does this work? Just like everything else, we use the null hypothesis. We start with the assumption that the variances are equal, which means we use the top line. But if the significance, the probability of being wrong if we do that, is less than 5%, we go to the bottom line instead. So in this case, we know that they're not equal, right? So we know we should be using the bottom line, right? So in this case, it's 0.013, less than 5%. So we reject the null hypothesis that they're equal, and we use the bottom line, which works out perfectly because that's what we knew we were going to use anyway, right? If this were more than 5%, we use the top line instead.